Hi, my name is Michael Alexander, and I'm a senior electrical engineering student at San Francisco State University. Today I'm going to be showing off the drawing robot from the Arduino engineering kit. Hope you like the video. This project is being built in the fall 2021 Mechatronics class at San Francisco State University, taught by Dr. Mojtaba Azadi. This class combines mechanical and electrical engineering practices, teaches us in detail about important components and control systems, and establishes hands-on experience simulating and building robots. In this class, we practice our hands-on experience using the Arduino Engineering Kit Revision 2. This comes with 3 robots: the webcam-controlled rover that avoids obstacles, follows paths, and lifts objects with a forklift. The second robot is the self-balancing motorcycle that balances and maneuvers using a flywheel. And the final robot is the drawing robot, and that's the one we will be demoing today. The drawing robot is a 2-dimensional cable-driven robot. It is programmed to take an image, process it, and then trace the lines with a marker to duplicate the image. This can be seen here. All right, let's talk about components. On this robot, there are 2 small DC motors that are connected to spindles wrapped in nylon wire, which are fastened on the other end in the 2 corners of the whiteboard. These motors have encoders which determine how many rotations have been done in order to determine the position of the robot. There is also a servo motor that operates the drawing aspect. It does this by holding 2 whiteboard markers and rotating to either set the black marker down, the red marker down, or no marker at all. There is a USB webcam, which using MATLAB support package, we can take images and directly import them into our MATLAB program. These images are then processed to be replicated by the drawing robot. In this robot, we use the Arduino Nano 33 IoT. This contains an ARM Cortex M0 Plus processor, an IMU sensor, and a Wi-Fi module. It's built for engineering projects and is able to run for long periods of time at low power. We also use the Arduino Nano motor carrier. This is a board that holds the Arduino Nano 33 IoT. With this motor carrier, we can control servo motors, DC motors, and stepper motors. It also has ports for other sensors and encoders and actuators available. In this project, it controls 2 DC motors, reads their encoders, and also controls the servo motor as well. The motor carrier uses the MATLAB support package for Arduino hardware. Now, with our robot built and connected to our computer, let's run some code. The first thing we have to do is initialize the Arduino, its motor carrier, and the servo. When these are initialized, we can control the positions of the servo motor to determine what the proper values are to set the left marker down and the right marker down. And then we can calculate a mean position to determine the no marker position. All of these values are then saved in a file. Next, we control the DC motors. We initialize them as well as their encoders. We can then run the motors for 3 seconds, and using the encoders on the motors, we can determine how many revolutions have occurred. Finally, we implement a closed loop control system to help maintain proper angular speed and position of the motors. This helps the machine not be too jittery when it's trying to reconstruct the images. Using the number of revolutions that occurred and some simple geometry, we can then create a coordinate system for the robot to move along. Using the information that we've measured up until now, as well as some initial position measurements inputted by the user, we can then choose any point on our coordinate system to move to. To do this, we then again initialize our Arduino, load up the servo positions that we found earlier, and we can run the code to move our robot to the desired position. We are not limited to moving to one position. We can actually move our robot to a sequence of positions. These sequences of positions will then become the lines that we use to replicate our image. However, we need to set some limits for where our robot can move. We first measure our board and then create an array of all possible spaces that the robot can move to. Using torque calculations, we can then calculate the torque needed to move the robot to each position. With these new torque values, we can then select a proper region for the robot to move in, where we can feasibly draw accurate images without error. These limits are then saved in a file. With everything initialized and our limits set, we are now ready to start replicating some images. The first image we will replicate is the MathWorks logo. MATLAB receives the image, processes it, and determines which pixels to keep. We can then create segments of these pixels to determine which path for the robot to draw along. We then reduce these segments for proper increments for the robot to draw. With our initial position inputs, we can then connect the Arduino and start drawing. With this file, we can run everything all at once. This file uses the image to pixel segments function as well as the draw image from pix function to create the MathWorks logo. The image to pixel segments function receives an image, binarizes it, creates coordinates for every pixel that it would like to keep, and then creates segments of these coordinates. The draw image from pix function takes in all of our initialization variables as well as the segments and gets ready to draw the image. It then initializes the Arduino and draws the image. I will now run this program and show the replicated MathWorks logo. The initial position that I set for each side is 30 centimeters. If we don't have an image file and instead would like to take a live image and replicate that, we can do that as well. First, we connect our webcam and take an image. We can then use that same image to pixel segments function to process our image and then create a graph of coordinates for our drawing robot. This program here will take in an image and then recreate it using the drawing robot. I will now run it to recreate the smiley face previously shown. Again, I have set each side to 30 centimeters. Here are the final two images recreated by the robot. Thank you so much for watching my video.